All right, so this is the only mathematic-related class that we will have in this entire semester. And then in this part of the lecture, we're going to look at the derivation of the Michaelis-Menten equation. Okay, so basically now we're going to get into enzyme kinetics. Okay, so before this class, we learned everything about how enzymes can catalyze reactions, right? How it is a tool to stabilize the transition state, etc. Okay, so that was more of a descriptive science. Now we're going to look at a little bit more of a quantitative science. Okay, now a couple of things that you should keep in mind. We're going to go over the derivation of Michaelis-Menten equation. Okay, but what's more important for you guys is how to use it. Okay, there are going to be two parameters that we're going to care about a lot. One is Km, the other one is Kcat. Okay, so these two are the most important kinetic parameters that we have for Michaelis-Menten equation. And then towards the end of the class, we're going to go over some inhibition. We have essentially reversible inhibition and then irreversible. But for the most part, we're only going to look at reversible inhibition because irreversible inhibition means that once a molecule binds, the enzyme is dead. It's irreversible. So we don't have to have any rate equation to describe that because it's dead. But if it's reversible inhibition, then we have to have some kind of equation to describe the inhibition. And then we'll have three types of inhibition. We have competitive, uncompetitive, and mixed. Okay, so we have three types of inhibition mechanism, you can call them. So we're going to look at enzyme kinetics. Okay, now before we go over to enzyme kinetics, the first thing that I want to talk about is probably going to be chemical reaction. Okay, so enzyme kinetics, again, kinetics, what are we talking about? We're talking about rate of reaction. Rxn stands for reaction. Okay, so for any chemical equation or chemical reaction, A plus B gives you, let's say, P stands for product. We know that there's going to be a rate constant, K1 or whatever, K. Okay? And then we also know that for any chemical reaction, essentially you will have a reverse rate. That's how you get to equilibrium, right? And the reverse rate is we're going to call it K minus 1, right? Then the rate of this reaction, we can say rate is equal to some K1 times the concentration of A times the concentration of B, and then minus K minus 1 times the concentration of P. Why do I go minus here? That is because K1 is the reverse reaction. Okay? So for any chemical equation or chemical reaction, generally that's what we write. Okay, now when we talk about enzymes, so this is general reaction, general chemical reaction. Now we're going to have an enzyme catalyzed reaction. And that's going to look a little bit different. Okay, now we have, okay, generally speaking, we're just going to call it S for essentially substrate or reactant, whatever you like to call it, plus E for enzyme. Okay, and then the first step of this reaction, still K1, K minus 1, you will generate this ES complex. So this is going to be the enzyme substrate complex. And then ES will then K2, K minus 2 become EP. So this is the enzyme product complex. And then EP, then we have K3, K minus 3, becomes E plus P, where P is the product. So this is going to be a generalized enzyme catalyzed reaction, right, where enzyme also participates in the reaction. Before we begin, there are several assumptions that we're going to make when we talk about this, because if you look at this multi-step process, you have K1, K2, K3, and etc. So the goal for us, okay, so our ultimate goal today is to get a rate expression. Rate is equal to some kind of K, okay, some kind of rate constant times some kind of a substrate concentration. So this is what we want, okay? So this is the kind of expression that we want to have in order to describe the rate of the reaction, okay? Why? Because we know for a fact that increasing substrate concentration increases the rate, okay? We know that, right? So obviously this is some kind of stuff that we want to get, okay? And then somewhere in here we will also have the concentration of enzyme factored in. But, you know, right off the bat, I'm just going to tell you that at the end of the Michaelis-Menten equation derivation, we will have an equation that looks like rate equals to some constant and then substrate. Okay, so I want to have rate as a function of substrate concentration. Assumption number one. Okay, like always in math class, you learn about, you make assumptions and then you change your equation somehow. Okay? Assumption number one is we are only going to look at the initial rate. Of reaction. Okay, so initial rate is very important. Right? Why do we only look at the initial rate? Because initial rate is a thing that we can measure. All right. Let's say you want to measure enzyme activity. You add the substrate, you add the enzyme, and then you're going to get a rate. You're going to start seeing a rate. Okay. So we look at just the initial rate. So the first part of that rate. Because obviously rate changes, right? But we're just going to look at the initial rate for now. Okay. And if we look at the initial rate, something happens immediately. All right. So again, we have E plus S gives you ES, gives you EP, gives you E plus P, okay? And remember this is K1, K minus 1, K2, K minus 2, K3, K minus 3, okay? Now, if we're looking at the initial rate, okay? If we're looking at the initial rate of this reaction, what happens, okay? Initial rate means that product concentration essentially is going to be very close to 0. Okay? That's just how it is, right? Because we're looking at the initial rate, right? Since we're looking at the initial rate, the concentration of product is 0, which then, okay, essentially we can drop some terms. We can drop this term. We can drop this, okay, because we don't have P. So then this equation simplifies into K1, K minus 1, ES directly goes to E plus P. Okay? So essentially we can ignore EP formation, okay, because we're looking at the initial rate. So that's essentially what we're looking at. We can combine these two together. Right? And we call this K2, K minus 2. So the initial rate. Also, because we're looking at the initial rate, another thing we want to know is that concentration of S is going to be much larger than the concentration, that change of S. Okay? The change in concentration of substrate is going to be negligible. So essentially, we're going to say that concentration of S is going to be some kind of constant. Okay? Because, again, we are looking at the initial rate. All right, we're going to go into assumption number 2. So we're going to go over the assumptions, and then as we're going over the derivation, you'll see where they fit in. All right? Now, assumption number 2 is what we call the rate limiting assumption. What does that mean? Okay, again, we have E plus S giving me ES, giving me E plus P. We have K1, K minus 1, K2, K minus 2. Okay. For the most part, enzyme and substrate concentration of the substrate is going to be much larger than the concentration of the enzyme. Think about this. Enzyme is a large molecule, right? And then the substrate is a small molecule. Right? So naturally speaking, you will not have more catalyst than your substrate, than your reactant. Right? So even in chemical reactions, we know that. Right? So here, essentially, we want to say that since for most reactions, substrate concentration is much greater than the enzyme concentration, okay, then we know that E plus S to ES, this one is going to be very fast. Okay? And ES then goes to E plus P. This one will be the rate limiting step. Okay? Because again, here you have a lot of substrates, so a lot of substrates very quickly just goes into the enzyme, and immediately you saturate all your enzymes with substrate. So the loading between enzyme and substrate is going to be a very fast reaction. Okay, it's like diffusion, right? So essentially, the first part is going to be a diffusion, right? So that one is not going to be the limiting step. Okay, so then we say here, this K2 is the rate limiting step, because K2 essentially here is the catalysis. So here it's just loading substrate to enzyme. The conclusion here is that the overall rate determined by ES to E plus P. And then K2, we give it a new name called Kcat. Okay? Kcat, right? The catalytic rate constant. Now, we went from assumption 1 that allows us to get rid of the EP, right? And then essentially simplify the overall reaction goes from E plus S becoming ES becoming E plus P. And then using the rate limiting assumption here, we say that because for the most part, substrate and enzyme concentration is very different, and then you have a lot of substrate. So substrate will load onto the enzyme via diffusion, and that's a very fast process. So we're just going to assume that the rate limiting step is to convert ES complex to E plus P. Okay? Because then essentially it's ES to EP, right? But again, diffusion is you don't have to worry about that. That's just faster than your enzyme. Now, we have the last assumption, assumption number 3, which is we're looking at a steady state. What does that mean? Right? Since we know that the concentration of S is much larger than the concentration of E, okay, what does that mean? And we know that S plus E become ES is a very fast process. Okay? Essentially, what this tells you is that the concentration of ES is constant until concentration of S becomes too low. Which this, for our derivation, doesn't happen because we look at initial rate. So essentially, here we want to say that ES concentration is constant. What does that mean? Steady state. That means that the rate of ES formation and breakdown equals. Okay? And then we'll use that in our rate derivation. Our goal for whatever E plus S becoming ES becoming E plus P, we have K cat, let's say K minus 2, K1, K minus 1. Our ultimate goal is to get a rate expression, or which is going to call it rate is equal to some kind of a catalytic constant times your substrate concentration. Okay, this is what we want. This is, this what we want. We know, okay, just from our assumptions, etc., we know that Kcat is the rate limiting. So since we assume Kcat is rate limiting step, essentially the rate becomes Kcat times ES. Okay. Why is that? Because we know that this is the rate limiting, okay? But of course, it's going to be Kcat times ES minus K minus 2 times E times P. But remember that P is equal to 0, right? Because from the initial rate. So then this term is out. So simply put, we just have a very simple rate. That is, the rate of the reaction is equal to the catalytic constant times ES, the concentration of EX complex. Now, what's the problem? The problem is ES is not a useful term for me, okay? Because I don't know, it's hard to quantify ES. Okay? Remember, I want to be able to quantify the rate based on the substrate concentration, not the concentration of ES. So we're going to do a little bit of manipulation here. Okay? All right? So we want to have, the concentration of substrate we want to describe the rate as a function of substrate concentration. So then what we're going to do is we're going to start with steady state assumption, which remember is ES is going to be equal to some kind of constant, which essentially says the change of ES concentration as a function of time is going to be equal to 0. So then what we have is that dES dt, so the rate of, remember that this is just the rate of ES formation and breakdown equals to 0. Okay, so rate, right? This is the change of ES concentration over time is going to be equal to 0. Right, so this guy is equal to 0. If we want to look at the rate of ES formation, what kind of terms do we have? Right, so ES is right here, right? Which rate, okay, which reaction give you ES? We have K1 and K minus 2. We have K1 ES plus K minus 2 EP. Right? So those are the reactions that produce Ks. Right? So they're going to give you Ks. So they're going to be a positive sign. Then the ones that will consume Ks will have a minus. Minus, obviously, K1 and K cat. Minus K negative 1 ES minus K cat ES. We know anything with a P is out. This guy is out from the top two. Right? This guy's out. So then equation simply becomes K1 ES minus K minus 1 ES minus K cat ES. So that simplifies it. And this guy is equal to 0. Now, we're going to do some arranging and stuff so that we're going to have some kind of a better expression. All right, so again, we're going to do some rearranging. K1 ES minus K minus 1 ES minus K cat. This is equal to 0. If we're going to move a couple of things, this then becomes K minus 1 ES minus K cat is equal to K1. Right, so I just essentially moved these guys to the other side. And then, as you probably can guess it, right, equal S, where's the K1? We're going to combine. So essentially, we're going to combine all constants. And this guy. We're going to call it Km. Okay? So this, we should call it the Michaelis Constant. Right? So remember at the very beginning of the slide, I said you have to know a couple of things that are useful, Km, Kcat. Right now, I already defined you what is Kcat, what is Km. Okay, so this is sort of the definition of Km, but don't worry, we're going to get to how to use it and how to make more sense out of it a little bit later, but just, bear with me, right? So right now, this is Km. And then E by itself is the concentration of the enzyme without the substrate. Okay, so this is enzyme concentration without, WO is without substrate. This guy is enzyme concentration with substrate. Okay, so ES complex versus E free enzyme by itself. In an actual experiment, ES and E is very difficult to quantify, okay, especially in their dynamic forms. Like how much of it is E, how much of it is ES. You don't know. Okay, so what do we say? We're going to define this thing called, so because in experiments, my ugly handwriting, it's hard to get information on individual E and ES concentration. So we have, essentially, we call it ET. Okay, not the space alien, ET meaning E total. ET is going to equal to E plus ES. So now, again, we have Km ES is equal to times S. Okay, so from here, we got this guy. And then we know that enzyme total is equal to E plus ES. Guess what I want to do? Take a guess. Okay. Remember, I want to get rid of concentration ES. That's what I want to get rid of. I don't want to see it anymore. So E here is equal to E total minus ES. This whole thing times by concentration S. Right? So that's still equal. And then we're going to break that out. We'll have E total S minus ES S. Okay. And then what you get is, so this is still Km enzyme complex. And essentially, what we'll have is, and then plus ES times substrate S. Okay? So then now I got rid of E essentially, and then now I have E, S, and then E total, and then substrate concentration. Now, I see now I understand why I'm doing this. Okay. So I have substrate concentration plus Km, right? ES. Okay? So just, put them together. And this, of course, is equal to enzyme total times this. Okay? Move it to the other side. I have now an expression for, ES, concentration of the ES. Okay? Because, again, here, because ES and E, they're difficult to quantify. Okay? ES and E is very difficult to quantify. So I want to be able to substitute ES, okay, any expression for ES as a E total term. Okay? So that's what I want to do. I want to transform ES into E total. Okay? So that's exactly what I did. So now I have an expression that says the concentration of ES is equal to concentration of enzyme total times substrate concentration divided by substrate concentration plus Km. Okay? Now, I got this. Okay? All right. Now, that one becomes very easy. Okay? So now we have somewhat of a manageable term for ES. Right? So then remember at the very beginning, what do we have? Our reaction is E plus S give you ES, give you E plus P. And this guy is K cat, K minus 2, K1, K minus 1, right? So that's our reaction. And remember we said that the rate is going to be equal to K cat, small k, cat times ES. Okay? We said that, right? We said that the rate of this chemical reaction is going to be governed by the rate constant Kcat times ES, right? Now we just got an expression for ES. Remember we said that ES is equal to E total times substrate concentration divided by substrate concentration plus Km. So then your V is then going to be equal to Kcat total enzyme concentration, substrate concentration divided by substrate concentration plus Km. Okay, so all of that just for this. Okay, now this is a lot easier to quantify, okay, because enzyme total is something you can measure. Okay, free enzyme by itself, difficult to measure. ES complex, difficult to measure. But enzyme total, I can measure. Okay, I can just find out how many enzymes I have total, regardless of whether or not it has the substrate inside. That's easy, right? So this is our Michaelis-Menten equation. Now, okay, we know, okay, that the maximum rate is reached when all E is in the ES form. Okay, so when enzyme total is equal to ES, okay, is equal to ES, what do you have? You have the maximum rate is equal to Kcat times Kcat times E total. Okay? So this is, we'll define this thing called Vmax, okay, the maximum velocity. Right? The maximum velocity is reached when, okay, when all of the enzyme is saturated by the substrate. Okay, so everybody, all enzyme is in ES form. So then, according to this rate equation, right? Because if ES is equal to ET, then you have Vmax is equal to Kcat times enzyme total. Okay. Now, so combining all of this stuff, we'll have the Michaelis-Menten equation, which is rate is equal to Vmax times substrate concentration divided by substrate concentration plus Km. Okay, so this is our Michaelis-Menten, oops, that's an N, equation. Okay? All right? So, Michaelis-Menten equation. Okay? Michaelis-Menten equation. Now, this equation, doesn't it look somewhat similar? Right? By the way, Vmax, this is a constant. This is a constant. Okay? Well, Vmax is not exactly a constant. It's just, again, remember, Vmax is equal to Kcat times total enzyme. This guy is a constant. So at any given condition where the concentration of the enzyme remains constant, then Vmax is constant. Okay, that's why I meant it's a constant. Okay, now, so what do you have? Okay, this curve, generally speaking, as a function of substrate, here we have V, which is rate. It's going to be looking something like this, where Here, this is Vmax. Okay? Right, so the maximum rate is achieved when your enzyme is completely saturated by the substrate. So as the substrate concentration increases to infinity, as long as you don't increase your enzyme concentration, then the rate is going to be limited based on the amount of enzyme you give it. Okay, so it's going to be limited at Vmax. Okay? Now, I want to show you something very interesting. Right? So if you look at Michaelis-Menten equation here, there's a special case where substrate concentration is equal to Km. Okay? Then what happens? Then your V is equal to Vmax, Km, 2 Km, Km cancel, Vmax divided by 2. Okay? So what that means is at 1/2 Vmax, the concentration that it corresponds to, this guy is Km. This is just like what we talked about in the hemoglobin binding, the loading, unloading process. Remember we talked about that KD thing, right? Do you guys remember at all? Hemoglobin rolling around like crazy, right? Hemoglobin, okay? So Km is a very useful number because it sort of tells you, okay? Essentially what Km tells you is how much substrate concentration I need to get to the half maximum rate. Okay, so essentially that tells you something, right? The larger the Km means that the more substrate concentration you have to give to this reaction in order for it to reach half the maximum rate. So it's going to be a crappy enzyme. Okay? Remember hemoglobin, right? When we said that a strong binding have a small KD, a large, weak binding hemoglobin or myoglobin or a weak binding globin, it's going to have a large KD. Remember that? Do you guys remember that at all? From like a month and a half ago? Okay? So it's the same thing, right? So which is why I'm telling you all biological behavior is all similar. It's just this enzyme loading, unloading. Okay? Now in this case, if you want to have a good enzyme, like an efficient enzyme, a very good enzyme, you want to have a very small Km because that means that only a little bit of the substrate is required to get to the half maximum rate. Right? So then you only need a little bit more to get to the maximum rate. Okay? All right? So are we good with this? So Michaelis-Menten equation. Now, yeah, I reserve all that space. Okay. So this is the Michaelis-Menten equation. So just memorize this. You're going to use this throughout your career if you're going to stay in the realm of biochemistry or biotechnology. You have the rate of the reaction is equal to Vmax. Okay? Vmax, the maximum velocity, and Vmax is dependent on kcat of the enzyme. Okay? Kcat is a constant. It's a characteristic of the enzyme times total enzyme. Okay? So if you want to change Vmax of a enzyme catalyzed reaction, what do? You add more enzyme. Okay? It's pretty simple, right? So if you want to change Vmax, the only thing you can do is add more enzyme. Okay? And then it's divided by Km plus substrate concentration. Okay? Km is Michaelis constant. Okay? It's set. Right? It will never change. Right? So you have two constants for every enzyme. Kcat, Km. Okay? Now, what I want to caution you is that here is a two-dimensional graph. Velocity as a function of substrate concentration, right? What if you have two substrates? Okay? Then you're going to have two of this graph. Okay, so depending on which substrate you're looking at, you will have 2 Km values. 1 Km value for each substrate. Okay? We're okay? Okay? Kcat doesn't really change because it's looking at the maximum. Alright? So just always remember that. Right? So Km, Kcat are constants at given conditions. Right? Now of course Km and Kcat, even though they're constants, but they are subjected to change depending on the condition of the enzyme. Okay? Because ultimately this is an enzyme catalyzed process. And last week we talked about how like enzyme use acid-base catalysis, how enzyme use electrostatic catalysis, right? So pH difference will cause a difference in catalysis, okay? Of course, right? Right? If you use acid-base and then the pH all of a sudden changes, then the rate of catalysis will change. Right? So even though here I say Km, Kcat are constants, yes, they are constants based on a particular condition. Okay? All right, so this is the Michaelis-Menten equation. All right? Now, experimentally, how do we get those numbers? Right? Back in high school, you probably did this rate experiment where you take, reactant A plus reactant B, and then you change the concentration of A, you change the concentration of B, and then you see how they affect the rate of your reaction, and then you can calculate the rate law. Remember that back in high school? You did that. I mean, I did it, so you must did it, okay? Now, for enzyme catalyzed reaction, a very typical experiment that you're going to do will be something like, I don't know, as a function of time, you look for concentration of substrate that goes down, right? Because as a function of time, substrate is going to get converted into product, okay? Now, again, we look for the initial rate, okay? We look for the initial rate. So maybe if the first 2 or 3 or 5 dots, depending on how linear they are. If it's a linear line, then we're looking for that initial rate. And that initial rate, we will get, so that's going to be a rate, right? Change in substrate concentration, change in time. Okay, so delta S over delta T, that's rate, okay? So initial rate, so for every condition that we do, these conditions differ based on the amount of our initial amount of the substrate that I put in. So for example, here I put 200 millimolar, here I put 100 millimolar, here I put 50 millimolar. Okay, and then we're going to run that reaction and look at how rate changes as a response of my substrate concentration. Okay, and then I get the rate, plot it over here where the velocity here, this is the rate that I calculate from my raw data, okay? And then this is my substrate concentration, meaning the amount of substrate that I added at the beginning. And then you will see this is going to be a Michaelis-Menten equation. Okay? You see how it increases rapidly and then eventually plateaus. Okay? So this is how you would experimentally determine your Km, Kcat. Right, so now, so in a summary, okay, so if I want to summarize what we've been talking about over the past hour, so these are all the different terms that we have. We have the initial rate of the reaction, so V naught. Right, so all of the V's that I wrote in my derivation, here I'm talking about V0, meaning the initial rate. We are only looking at the initial rate, okay? All right, so we're only looking at the initial rate. And then we have the maximum velocity, Vmax, Km, Kcat. Okay, so Vmax, Km, Kcat, no problem, right? Vmax is the maximum velocity. It doesn't have a special name, just the Vmax, right? Km is called Michaelis-Menten or Michaelis Constant. And typically it is associated with enzymes' affinity for the substrate. Okay? Just like what? Just like hemoglobin or myoglobin. Okay? Just like that. Remember we say in myoglobin, it binds oxygen very tightly, right? Right? So, that's we were looking at the KD for myoglobin. This is pretty much the same thing. Km, smaller the Km, meaning that this enzyme is very efficient at grabbing the substrate. Okay? All right? We're okay with this? Okay, 有听懂 Smaller the enzyme means that this enzyme is more efficient at grabbing the substrate. Okay, now, Here, oh yeah, by the way, kcat is called turnover number. Check out the unit real quick. The unit here is 1 per second, meaning per enzyme. Okay, so how fast this enzyme can react the substrate. So let's say you have kcat of 2, meaning that per second, okay, per second, in 1 second, every 1 enzyme you have, you can react to substrate. That's just what it means, turnover number, okay? Now, what I want to draw your attention is this, the catalytic efficiency, okay? So if you want to have a very fast enzyme, okay, very fast enzyme, you want to have small km and large kcat. Larger the kcat because kcat directly influence your Vmax. Vmax directly influence your rate, your V, okay? So larger the kcat, faster the process, faster the enzyme, regardless, okay? Km, same thing. Smaller the km means that the better the enzyme at this particular substrate, okay? Because it means that this enzyme can very easily grab the substrate and react, okay? So Km, kcat. Km is more associated with binding. Kcat is more associated with the actual catalysis, the rate of the catalysis. Okay? Km, kcat. Right? So you should know. Now, so we have, of course, kcat want to be large as possible. Km you want to be as small as possible. So you divide kcat over km. This will give you the catalytic efficiency, okay? So this is sort of like a description for the overall efficiency of an enzyme acting on a substrate, okay? Obviously, for the different substrates, you will have a different catalytic efficiency, okay? Sometimes an enzyme have 2 substrates, then you will have 2 of those numbers, okay? Because Km obviously will be different, okay? Now, kcat over km has an approximate upper limit around 10 to the 8th to 10 to the 9th power. Why is that? Because that's sort of the limit of diffusion. Once your enzyme go beyond that, then our initial rate and our whatever, the rate limiting assumption doesn't hold anymore. Okay? That means that the enzyme itself is not limiting. The diffusion is. Okay? So that means that your enzyme cannot do anything else. Okay, it just can't. You're limited by diffusion. Okay? Do you guys understand what I'm trying to say? Okay? Maybe okay? Now, how do you experimentally determine Km and kcat? You do this experiment, and this is the line that you will get. Okay? And well, ideally, okay, you have some expensive computer program that would do a nonlinear regression, and then you're done. Okay? But that's current day. Without our advancement in computation, you can't do that, right? Right? So, like 50 years ago, there's no nonlinear regression to do this. Okay? So, long time ago, what people have to do is they have to transform. They have to transform the data into a linear line, okay? And essentially, how do you do it? All you have to do, there are a couple of ways of doing it. The most common way to do it is the Lineweaver-Burk plot, where you would just do a double reciprocal plot, okay? Double reciprocal plot, where remember our V is equal to Vmax times substrate divided by Km plus substrate. So then what you would have to do is take the inverse of both sides, and that's what you'll get, okay? And then you would just plot 1 over V versus 1 over S, okay? If you plot 1 over V versus 1 over S, then you will get a linear line, okay? Because this essentially is going to be a constant. This is going to be a constant, okay? So then you'll get a linear line that looks like that, right? And a couple of things, the slope, right? The slope here is Km over Vmax, right? And then the y-intercept is 1 over Vmax. So this is very easy for you to determine what the Vmax is. Once you have the Vmax, you can calculate what the Km is. Or you can also get the x-intercept, right, which is minus 1 over Km. Okay, you can do that too. Now, there's going to be a limitation to this thing. Where's the limitation? As you can see, most of the dots are focused sort of in the middle. It's very difficult to get an evenly spread out line. That's just very difficult. Why? The substrate here is 1 over S, right? So the lower the S, the more dots here, right? But then it's very difficult to calculate the rate when your substrate concentration is so small. Why? Because the second you add your substrate, and then your measurement is not quick enough, and then you don't see it. You cannot see it. Okay? And remember, we are looking at the initial rate. Okay? We're looking at the initial rate. Now, initial rate works when, remember, we say that substrate concentration is much larger than enzyme concentration. Okay? Now, if your substrate concentration is very, very small, then that assumption may not be okay anymore. Okay? So the rate that you calculate from such an experiment may not be very accurate. Okay? So in addition, it's hard to do. It's not very accurate. Right? Also, you cannot possibly have this guy. Okay? You cannot have negative substrate concentration. Okay? So this is great. Okay? So I don't know if our biochem lab will make you do this, but I think we should. You will be able to do some enzyme catalyzed reaction, measure it, calculate the rate, based on the rate, get the Vmax, therefore Kcat, and Km. Okay? And using the Lineweaver-Burk plot. All right, so that's okay. But just like I said, nowadays, okay, there are a lot of graphing softwares, like Origin, for example. You can just put in the data, select the nonlinear regression that you want to use, and it's going to fit the data for you. Right? It's a lot easier. Okay? Are we okay with this? All right. Now, a couple of things. Here, I want to just give you an example. This table is in your book. I just want to give you some examples of some of the common Kcats over Kms. Some are really, really fast. Some are really, really slow. Okay? For example, Chymotrypsin is a horrible enzyme. Okay? Because if you take a look at it, Kcat is 0.14. Right? And although the Km is not too bad, okay? And the catalytic efficiency turns out to be 9.3, right? And as you go, better and better, you have enzymes that can get to, like fumarase, 10 to the 8th power. So for example, fumarase is, about as fast as you can go for enzymes. Carbonic anhydrase, same thing, 10 to the 7th. That's, almost reaching the limit, okay? So obviously, Kcat over Km varies a lot between different enzymes. Okay, so don't be surprised that you have an enzyme, but it sucks. Okay, maybe it's because the Km is too high, Kcat is too low. Remember last time I sort of explained or introduced to you guys what I do in my lab, based on substrate promiscuity to catalyze different reactions, right, to build synthetic metabolic pathways. Okay? Now, we said substrate promiscuity, right? Or you can also say substrate specificity. Okay? Promiscuous meaning it's able to accept many different substrates. Specific meaning it's, very specific. Doesn't matter. 两个都是一样，都在讲同样的东西啦。Okay? Now, substrate specificity. Okay, let's take a look. This is chymotrypsin. Okay? Preference of chymotrypsin in the hydrolysis of several N-acetyl amino acid methyl esters. Right? So their substrate, their model is not peptides per se because it's hard to measure. Here they use a model substrate, amino acid methyl ester. Okay? And we know that chymotrypsin likes to cut bulky R group amino acids. Right? So what you can see is that for phenylalanine, So kcat over kn, phenylalanine 10 to the 5 because it's really bulky. Norleucine or norvaline, those two are valine and leucine derivatives. You can see still pretty good, 10 to the third power, 10 to the second power. Okay? Glycine, okay, glycine, it sucks, it's 0.1. Okay? So obviously kcat over km will also tell you a little bit about substrate specificity. So last week I didn't show you this. Remember I said, you know, I tested 6 different enzymes for a specific reaction that I want. What I didn't show you is I actually did test or calculated the kcat and the km. Okay? So after I calculate kcat and km, I can then calculate the catalytic efficiency for the different enzymes on the different substrates. Okay? So this is something that we routinely do when we encounter a new enzyme that we want to characterize. Okay? And then you'll see how specific this guy is. Okay? All right, are we okay with this concept of enzyme specificity? Now, a non-specific enzyme will have, you know, similar kcat over km for different substrates, but a very specific enzyme will only have a large kcat over km for one substrate, and then the others are going to be small values. Okay? All right, now, so in this case, the observed effect of an amino acid mutation in an enzyme active site on Km and Kcat can be used to identify the role of the amino acid in substrate binding, Km effect. Okay, so substrate binding, we essentially can call it the Km effect, and the transition state stabilization, we can call it the Kcat effect. Okay, so just again, okay, Km is more related to substrate binding. Kcat is more related to the actual catalysis. And what's the actual catalysis? How to stabilize the transition state. Okay? So now do you have a feeling of what the two constants are sort of, what they are now? Okay? Km, substrate binding, just like hemoglobin Kd. Okay? And Kcat is more like the actual catalysis. Okay, like how well does the enzyme stabilize the transition state? Okay?